All right, so we've got two papers for you today. And get this, they're both by Albert Einstein from 1935,
Yeah.
back in 1935.
2 months apart.
Yeah, 2 months apart. And the thing is, Einstein himself, he didn't actually connect the dots between them at all.
Right.
He really thought they were about completely different things.
Separate worlds of physics, yeah.
Exactly. One was all about quantum mechanics. That's the rule book for the super tiny, the really, really small stuff.
Right, the microscopic.
Yeah, exactly. And then the other paper was tackling the huge scale of the universe, like gravity and space-time itself.
The realm of general relativity.
Exactly, general relativity. And here's the kicker for you, and then this is what makes this so exciting. A bunch of scientists, now they're starting to think that these two papers, they're actually deeply connected.
Yeah.
And that's kind of mind-blowing, right?
Well, it is. It's really profound because it's hinting at this fundamental link, between how the smallest bits of reality work and the grand structure of the entire universe.
Yeah, it's like they're two sides of the same coin.
That's a good way to put it.
And that's what we're going to dive into today in this deep dive, just for you.
Your express route.
Exactly. It's like a shortcut to understanding this cutting-edge area of physics.
It really is. And to appreciate how we got here, it's helpful to think about the historical context for you.
Okay.
For centuries, Newtonian physics reigned supreme.
Yeah, the clockwork universe.
Yeah, exactly. The idea was if you knew where everything was and how fast it was moving, you could predict the entire future.
Like a perfect machine.
Precisely.
Yeah.
And it worked incredibly well for everyday stuff, like planets orbiting stars.
Yeah.
But then in the early 20th century, physicists started looking at the really, really tiny stuff, the microscopic realm. And that's when things started to break down.
It's like Newton's laws just couldn't keep up.
They just didn't apply anymore. It's a whole new ballgame.
Yeah, and that's where quantum mechanics comes in, right?
Absolutely. It was this incredible period of intellectual ferment, and these brilliant minds came together.
Yeah, like Planck, Bohr, Heisenberg.
Schrödinger, Born.
Yeah,
they really revolutionized physics.
And they created this whole new way of understanding reality, right?
They did. And one of the key things for you to grasp is that there was this massive shift from certainty to probability.
Okay, so instead of saying, this is definitely going to happen,
quantum mechanics says, here's the likelihood of this or that outcome.
So it's all about possibilities.
Exactly. It's all about probabilities. It's a very different way of looking at the world.
Yeah, and Einstein, even though he was a major figure in the early days of quantum theory,
right,
he always felt like it wasn't the whole story.
He had this gut feeling that it was incomplete.
Yeah, like it was a stepping stone to a deeper understanding.
Exactly. And that's a really important point for you to understand about Einstein's mindset.
Okay.
He famously said, God does not play dice.
Yeah, I've heard that one.
And that quote really captures his deep discomfort with the randomness at the heart of quantum mechanics, you see.
So it wasn't that he thought quantum mechanics was wrong?
No, not at all. His predictions were and still are amazingly accurate.
It just didn't sit right with him.
Right. He believed that eventually a more fundamental theory would emerge for you.
One that didn't need probabilities.
Yeah, one that would restore that sense of determinism that Newton had given us.
Okay, so he was kind of hoping to find flaws in quantum mechanics.
He was. He actively tried to expose inconsistencies within the theory.
And that leads us to the first paper we're looking at today.
The EPR paper.
Exactly. Published in May 1935.
Co-authored with Boris Podolsky and Nathan Rosen.
Right. So Einstein, Podolsky, and Rosen, they thought they'd found a major weakness, a potential Achilles heel of quantum mechanics.
Through this very strange phenomenon called quantum entanglement.
Entanglement. Yeah, I think a lot of people have heard that word, but let's break it down for you.
Okay.
So imagine you're flipping two coins.
Right.
In our everyday experience, each coin is going to land on either heads or tails completely randomly.
Right. They're independent of each other.
Exactly. Now, here's where quantum mechanics gets really weird.
Okay.
In the quantum world, before we look at a particle, it can actually exist in this blurry state called a superposition.
It's like the coin is both heads and tails at the same time.
Until we actually observe it.
Right. The act of measurement forces it to choose one state or the other.
So imagine now that you have two particles that are entangled.
They've interacted in a way that links their fates.
Okay.
Even if you separate them by a huge distance.
It's like across the galaxy.
Yeah, potentially even further. Their destinies remain intertwined for you.
So if you measure one particle and find out, let's say its spin is up.
The other particle instantaneously has to have the opposite spin down.
And that happens no matter how far apart they are.
It's as if they're communicating faster than the speed of light.
Yeah, that's what Einstein called spooky action at a distance.
He really didn't like that.
Yeah, it just seemed to go against everything he knew about the universe.
It violated his intuition about the independence of objects that are far apart.
And that no influence should be able to travel faster than light.
Right. It was as if there was some invisible thread connecting these distant particles.
But Einstein also had another problem with entanglement that he found really unsettling.
Yeah, he was also bothered by the fact that in quantum mechanics, you can know everything about the combined state of two entangled particles, but know nothing specific about the individual properties of either particle until you make a measurement.
So it's like knowing you have two gloves, a left and a right.
But not knowing which glove is which until you look.
Yeah, and that really bothered him.
It struck him as deeply problematic for you.
I can see why that would be confusing.
It is. It's one of those things that really makes your head spin.
And if you're feeling a bit lost right now, you're not alone. A lot of people struggle with this.
Even physicists.
Yeah, we can use entanglement in technology, and we can predict its effects with incredible accuracy,
Right.
but actually understanding what's really going on.
That's a different story.
It's like our intuition just can't quite grasp it.
The key takeaway here is this concept of non-separability.
Okay.
Entangled systems are fundamentally linked in a way that classical physics just doesn't allow for.
So going back to the EPR paper, what was Einstein really trying to achieve with that?
He wasn't just trying to point out the spookiness for you.
Okay.
His real goal was to expose a contradiction within quantum mechanics itself.
So he was trying to prove it was wrong somehow.
In a way, yes. He was trying to show that it was incomplete, that it couldn't be the whole story.
And how did he plan to do that?
Through a thought experiment involving entangled particles.
Okay.
They proposed that by carefully choosing what to measure on one particle, either its momentum or its position, you could indirectly gain knowledge about the corresponding property of the other particle without actually measuring it.
Okay, so because you could choose to measure either momentum or position on the first particle.
It seemed to imply that the second particle must have definite values for both momentum and position all along, even before the measurement.
And wouldn't that violate Heisenberg's uncertainty principle?
Exactly, because the uncertainty principle states that you can't know both the precise momentum and position of a particle simultaneously.
So Einstein was basically saying that if a measurement in one place can tell you something about a particle far away instantly,
Then that distant particle must have already had that property for you.
like it couldn't have just popped into existence when you measured it,
Right, the measurement shouldn't magically create that property in a distant location.
and that felt wrong to Einstein.
It just didn't make sense to him.
So what happened with the EPR paper? Did it achieve its goal?
It became incredibly influential, but Einstein himself wasn't completely satisfied with it.
Wait, why not?
Well, Schrödinger wrote to him congratulating him on the paper.
Okay.
But Einstein's reply is quite telling. He felt that his main point got buried in all the technical details.
So it didn't quite come out the way he wanted.
Yeah, he felt like the paper didn't fully capture his intended message for you.
Interesting. And what was that message?
Well, Lenny Susskind, a very prominent physicist, has argued that Einstein's real concern was with the nature of physical reality itself.
What does that even mean?
It's a deep philosophical question about what is real.
Right.
What exists independently of our observations? You know,
Okay, so it was more than just about the uncertainty principle.
it was about the very foundations of reality for you.
Okay, so that was May 1935. Now, let's jump ahead just 2 months to July 1935.
Another Einstein paper.
Yeah, another one. This time it's just him and Nathan Rosen.
Right.
And this one seems completely different. It's about bridges in space-time.
Yeah, these are now known as Einstein-Rosen bridges, or more popularly, wormholes.
Wormholes, yeah, I've heard of those too. But to understand them, we need to talk a bit about general relativity,
Absolutely, Einstein's masterpiece from 1915.
which totally changed our view of gravity, right?
It completely revolutionized our understanding for you.
Okay, so before Einstein, we had Newton's idea of gravity as this force acting at a distance.
Yeah, like the Earth pulling on the moon.
But Einstein came along and said, no, it's not a force, it's about the curvature of space-time itself.
Exactly, caused by mass and energy.
Okay, so imagine like a bowling ball on a stretched rubber sheet.
Yeah, that's a good analogy.
The bowling ball creates a dip, and that dip influences how smaller objects move around it.
It's a simplified picture,
Right.
but it helps to visualize how gravity works in Einstein's theory for you.
So gravity is like warping the fabric of space and time.
Precisely. And shortly after Einstein published his theory, Carl Schwarzschild found this remarkable solution to his equations.
Okay.
And his solution described the space-time around a spherical object, like a star.
And that led to a pretty startling discovery.
It did. Schwarzschild showed that if an object is massive enough and collapses to a small enough size, the curvature of space-time becomes so extreme that it creates a point of no return.
The event horizon.
Exactly. Nothing. Not even light can escape from beyond that horizon.
And we call those black holes, right?
We do. They're regions of space-time where gravity is so strong that nothing can escape.
So in their 1935 paper, were Einstein and Rosen specifically talking about black holes?
Not explicitly, but the math they were exploring turned out to have deep connections to black holes for you.
What did they actually find?
They discovered a theoretical way that two black holes could be connected in space-time
Connected like how?
by a tunnel or a bridge.
Like a shortcut.
Yeah, you could think of it that way. Instead of having to travel vast cosmic distances through normal space, you could potentially pass through this wormhole and emerge in a totally different location.
So it's like folding that rubber sheet we were talking about earlier.
Yeah, exactly. You fold it so that two distant points touch, and you create a shortcut through warp space-time for you.
That's pretty wild. But at the time, was there any link between these wormholes and quantum entanglement?
Not at all. They were considered completely separate areas of physics.
But that's where things start to get really interesting.
Yeah, because in recent years, there's been this amazing new proposal.
That wormholes and entanglement are actually connected.
Exactly, and it's a profound idea that has huge implications, not just for our understanding of black holes, but for the very nature of space and time.
So how did this connection come about?
It started in the 1970s with Stephen Hawking's work on black hole radiation. Contrary to what we used to think, Hawking showed that black holes aren't completely black.
Wait, so they don't just suck everything in?
They do, but they also emit a faint thermal radiation from their event horizon.
So they kind of glow a little bit?
In a way, yes, and here's how it works in the quantum world. Pairs of virtual particles and antiparticles can just pop into existence, even in empty space.
Out of nothing.
Well, sort of. They borrow energy from the vacuum,
Yeah.
and usually they quickly annihilate each other.
Okay.
But near the event horizon of a black hole, something really interesting can happen.
What?
One particle of the pair can fall into the black hole, while the other escapes and radiates away into space.
So it's like the black hole is slowly losing energy.
Exactly. And here's the key point for you. Those pairs of particles, even when they get separated, they're entangled.
So even though one falls into the black hole and the other escapes, they're still linked.
They are. They share this spooky connection.
And this led to a big problem, right? The black hole information paradox.
It did, because Hawking radiation carries away energy from the black hole, causing it to slowly shrink and eventually evaporate completely.
And that creates a problem because one of the fundamental principles of physics is that information is never lost.
Right. So if something falls into a black hole, where does the information about that object go if the black hole disappears?
That's a good question.
It is. And Hawking's initial calculations suggested that the emitted radiation was just random thermal radiation.
So it wouldn't carry any information about what fell in.
Right, which created a conflict with quantum mechanics, because in quantum mechanics, time should be reversible and information should be retrievable.
So how do we resolve that paradox?
That's where the holographic principle comes in.
Okay.
This was a really radical idea championed by Leonard Susskind and Gerard 't Hooft.
What did they propose?
They suggested that all the information contained within a volume of space could actually be encoded on its two-dimensional boundary.
Like a hologram.
Exactly like how a hologram stores a three-dimensional image on a flat surface.
So all the complexity of the universe could be encoded on some kind of cosmic boundary.
That's the idea. And Suskind's work in string theory actually led him to this insight.
How so?
He realized that if you probe a fundamental quantum string with more and more energy, it actually appears to spread out in space.
So it's not really a point-like particle?
No, it's more like a fuzzy, extended object.
Interesting. So the information isn't localized in the way we usually think.
Right. It's more spread out, maybe even stored on the boundary of the system for you.
Okay, so the information about something falling into a black hole could be encoded far away on the event horizon.
Or even further out, potentially.
Okay, but the story doesn't end there, does it?
It doesn't. In 2012, a group of physicists published a paper that presented a new challenge to our understanding of black holes.
This is the AMPS paradox, right?
It is named after the authors Harry Marolf, Polchinski, and Sully.
And what was their paradox?
It focused on the entangled nature of Hawking radiation. For that outgoing radiation to carry information about what fell into the black hole, the early radiation and the later radiation would also have to be entangled with each other, for you.
Okay, but I thought you said entanglement was like a one-to-one connection.
It is, and that's the problem. Quantum mechanics has this rule called the monogamy of entanglement.
Which means?
A quantum system can't be maximally entangled with two independent other systems at the same time.
So it's like having one phone line. You can only have one clear conversation at a time.
That's a good analogy, and this created a crisis for our understanding of black holes.
Because it seemed like the entanglement needed for information to be preserved was forbidden by quantum mechanics.
Exactly. It was a real puzzle.
So how did they get out of this mess?
This is where the truly mind-blowing proposal of ER EPR comes in.
Okay.
This was put forward by Juan Maldacena and Leonard Susskind.
ER equals EPR. What does that even mean?
Well, ER stands for Einstein-Rosen bridges, or wormholes,
Right.
and EPR stands for Einstein-Podolsky-Rosen, the entanglement paper we talked about earlier.
Right.
Their radical proposal was that these two seemingly distinct phenomena are actually equivalent for you.
Equivalent, how so?
They said that if two regions of space are entangled at the quantum level, there must be a wormhole connecting them,
Even if those regions are super far apart.
even if they're on opposite sides of the universe.
So entanglement creates wormholes.
That's the idea, and it's a really profound one because it completely changes how we think about both entanglement and wormholes.
Okay, so let's go back to the black hole paradox. How does ER EPR solve that?
Remember that the distant Hawking radiation escaping the black hole is entangled with something inside the black hole.
Yeah.
According to ER EPR, that entanglement implies a wormhole connecting the radiation to the black hole's interior.
So the information isn't lost, it's traveling through the wormhole.
Exactly. The information is encoded in the entanglement, and that entanglement creates a bridge, a wormhole connection.
So the distant radiation isn't really that distant after all.
Not in this entangled reality for you.
It's amazing that Einstein published his papers on entanglement and wormholes just 2 months apart.
It is, and he probably had no idea that they were connected in this way.
But the story goes even deeper, right?
It does. Mark van Ramsdonk did some really interesting work that takes this even further.
What did he do?
He used the holographic principle to explore the relationship between entanglement and the structure of space-time itself.
Okay, so he was thinking about space-time as a hologram.
Yeah, and he imagined that the underlying quantum system resided on a boundary.
Like the surface of a sphere.
Right, and he asked this fascinating question. What happens if you theoretically snip the threads of entanglement between different parts of that quantum system?
Snip them. How?
Just imagine you could somehow remove the entanglement between those regions.
Okay.
And his calculations suggested that if you do that, the corresponding regions of space-time would literally start to pull apart.
Like the fabric of space is being torn.
In a way, yes, and they could even become completely disconnected.
So entanglement is holding space-time together?
That's what his work suggests, and it's a revolutionary idea for you.
It is. It's saying that entanglement isn't just some weird phenomenon happening within space-time.
It's saying that entanglement might be fundamental to the very fabric of space-time itself.
So space itself might emerge from this network of quantum entanglement.
That's the mind-blowing implication.
Wow. So where does all this leave us in our quest to understand the universe?
Well, it's challenging the traditional approach of trying to quantize gravity, you know.
Applying the rules of quantum mechanics to Einstein's general relativity.
Exactly. But this new research is suggesting that maybe quantum mechanics and gravity are already intertwined from the get-go.
Like they're two sides of the same coin?
That's a good way to put it. And it's possible that quantum mechanics has been knowing about space and gravity all along in ways we hadn't realized.
So we might have to rethink everything.
We might, and it all ties back to those two seemingly unrelated papers that Einstein published in 1935.
It's incredible how much those papers have shaped our understanding of the universe.
They've really opened up entirely new avenues for exploration.
So here's a final thought for you to ponder.
Okay.
What if space itself, the very arena in which everything happens, isn't a pre-existing stage, but rather a manifestation of quantum entanglement?
That's a truly mind-bending idea.
It is. It means that the very fabric of reality might be woven from these spooky connections between quantum particles.
It all started with Einstein's papers and the realization that they're deeply connected in ways he could never have imagined.
So the revolution in our understanding of the universe continues, and it's full of surprises.
It is, and it's all about these unexpected connections that are changing how we view reality itself for you.
And who knows what other amazing discoveries await us as we continue to explore the mysteries of quantum gravity holography and the profound implications of ER EPR.
It's an exciting time to be a physicist.
That's for sure.
And who knows, maybe one day we'll fully understand the deep connection between the very small and the very large.
I can't wait.
Me neither.
This is incredible stuff.
It is. It really is.
Thanks for joining us for this deep dive into Einstein's mind-blowing papers.
My pleasure. It's been a fascinating journey.
And until next time, keep exploring the universe.
And keep wondering about those deep connections.
You never know what you might discover.
That's the beauty of science.
Absolutely.
Always more to learn.
Always more to uncover.
Yeah, it's a never-ending adventure.
And that's what makes it so exciting.
Absolutely.
All right, thanks again, and see you next time.